Okay. All right. So, what is the boiling point of a sugar solution at atmospheric pressure? How do we calculate boiling point elevation? So, boiling point elevation can be calculated with the Van Hoff equation. So here we have the Van Hoff factor, or not with Van Hoff equation, but with our boiling point elevation equation. So this is proportional to the number of species in solution. Okay, so for sugar, I equals 1. As a couple other examples, so for NaCl, which goes to Na plus Cl minus, I equals approximately 2. For calcium chloride, which goes to calcium 2 plus 2 Cl minus, I is approximately 3. So it's roughly the amount of species that are in solution. But for sugar, it doesn't dissolve into anything, so it just stays as sugar, so I is 1. This is Kb, is our mole boiling point constant, which is computed for our solvent. So it's just R, which is the gas constant, times the normal boiling point of the solvent, times the molar mass of the solvent, over the delta H vaporization for the solvent. Okay, so these are all solvent terms. So for water, the gas constant for any species is 8.314 joules per mole Kelvin. Our boiling point for water, I'm going to use as 373.15 Kelvin, or 100 degrees Celsius. Our molar mass for water is 18.02 grams per mole. And, and that should be squared, sorry. And our delta H vaporization for water is 40.66 kilojoules per mole. So then our Kb constant for water is 8.314. In retrospect, probably should do this a little lower. So our Kb for water is 8.314 joules per mole Kelvin, times our temperature, our boiling point, times our molar mass, and then divided by our delta H vaporization. And now checking on some unit cancellations here. So we've got this per mole can cancel there. This we're going to need to multiply by 1,000 joules per kilojoule to cancel that and cancel that. And then one of these kelvins will cancel with this. And so what we're going to end up with in the end is a gram per Kelvin mole as our unit. So if we run this through on our calculator, we get 513.06 gram, we're going to get gram Kelvin per mole. So the Kelvin will be on top. or if we multiply by a kilogram per 1,000 grams, 0.51306 kilogram Kelvin per mole. And now if we return to our temperature change equation, then we have pretty much all the factors we would need for a sugar solution. So our delta TB is going to be, so just rewriting it, I KBB, which is just 1 times 0.51306 kilogram Kelvin per mole times B. Now B is the molality, which is in moles, I guess I'll write it here actually. It's the moles of solute over the mass of solvent. So if we had a sugar solution that was 1 mole per kilogram, so there was 1 mole of sugar per kilogram of water, then our delta TB would be 0.51306 Kelvin. So our boiling point would be raised by 0.51306 Kelvin. And so to put it more, to hammer it home even more, our final temperature, as it's our delta T, our final temperature minus our initial, which would just be the normal boiling point, would be equal to this 0.513 or 0.51, just to round it to 2 decimal places. And so our boiling point of our sugar solution would then be, so moving this to the other side, would just be 373.66 Kelvin. So now, so a sugar solution that was a mole per kilogram would boil at 373.66 Kelvin. And we can use this same constant for any molality, and so all you need to do is figure out the new molality. Okay, so if we check here, so we've got, here's our boiling point equation, and here's each of the factors. So for sugar, we have I equals 1. So our KB, you can also just look up these values. It's about the same, 0.513, 0.515. And depending on the molality you're given, you would get a different value for your elevation. And of course, depending on the units. So that looks good.